All right, we continue with the last talk of this morning session. It's a great pleasure to meet Atsushi Takahashi, who is going to tell us about generalized Frobenius manifold, Frobenius manifold generalizable system of thinking. Thank you.
Well, thank you very much for the introduction, and it's my great pleasure to give a talk in this Homological Symmetry conference. So I'd like to thank organizers for giving me an opportunity. So let me start from the this is my motivation. So I'd like to clarify certain conjecture one-to-one correspondence among triangular categories with great exception operator, generalized group system. It is some homological aspect for the Otani group level of the part one, and things in performance structures. And the first one, the relationship between the first one and third one is known as Dubrovin's conjecture. And so one of the problems is to make this precise mathematical statement, for example. And in particular, by thinking, so for the Frobenius manifold, as an example, we interested in, or we want to study this relation and this relation to regions based on stability conditions, or so the five categories studied by constants. But today, unfortunately, we don't discuss some categorical part and more the space of stability conditions. But I explain some elementary part of this story. Okay, so first I like to explain notion of generalizable system. So in order to do that, I need to prepare the definition of the lattice statement. So it is a slight generalization of the usual one, which you can find in a Berkeley's textbook. So I explain the definition. So the lattice statement consists of variable n, I, and delta. And here n is a free model of rank mu, and I is a symmetric dividing form, and delta is a subset of n for the set of reality. So here I put RE to mean the real. So therefore, in the condition, the second one, I assume that the length of the real root is 2 for anything delta. And so this is almost a usual definition after some point. So and so here, based on this data, we can define also a variable as usual. And it is a group generated by a reflection with respect to a real group. And a practice not the usual one, I think. So, first, it is a technical remark. So today, in the previous definition, I used the symmetric binding form. So therefore, we only consider simply this one. And the second one is the real form. This is very important. So I don't assume that the I is positive. This is different from the notion in the Berkeley's book. So therefore, the story is very, very rich. And also, based on this remark, so therefore, the while group is not necessarily a Coxeter. So in the usual case, one property of the while group is that it is a Coxeter. So therefore, we need an implicit definition of a Coxeter which does not depend on a particular presentation with W. So this is very important. So here in this setting, at first sight there is no definition of a Coxeter, or we don't know how to define it. But later, by introducing the notion of the root basis, we can define a notion of Coxeter. And so here, so because I didn't assume I is positive degree, the one important ingredient of the root set will be the signature. And I identify mu plus and mu zero and mu minus. The number of positive and zero negative eigenvalues of phi. And in particular, this mu zero is nothing but the rank of the value of I. And so there are several finiteness conditions, but it turns out that they coincide. This is a statement. So for root system, so these conditions are equivalent. So the first one is nothing but a positive definiteness of I, and the second is the finiteness of the root, and the third one is the finiteness of W. So they are equivalent. So we say satisfying these equivalent conditions are finite root system. Or sometimes it is known as a classical root system compared to the other one. So it is in the remark. So the notion of the previous root system contain these important classes. For example, finite root systems, elliptic root systems, and Caspian. And what is important in our story or in studying Frobenius structure or some category for starting, the last one is very important, but unfortunately at the present we don't have a good name, so I cannot specify the last one, but it is important. And also, the irreducibility and small and so on are not very defined. So we can say about classification. So, and in the finite case, the classification we use to the usual one. And so you can find it in the Prototype book, okay? And but here I put the definition of how to construct them for A and B, because this description will be very important later. Or so this some is quite related to the geometric construction of the racing system. Probably in the B case, the condition on N1 plus and mu is even number, even integers. You find this exactly the same condition in the geometric construction root system. So unfortunately, or we cannot say something about the mu today. And so now we can introduce the notion of the root base. And so we consider a subset of root such that the set of root is generated by B some under the orbit of WB. So WB is a subgroup of Weyl group generated by these mu groups. So this is a generalization of the usual root base. So if the root admits a notion of the positive, positive root or negative root, then we can find some root basis consisting of the simple root. So it's some generalization of the notion of the some simple basis. And categorically, it will be almost the equivalent to the free exception correction up to the translation. But I don't discuss in detail today. And from this condition, it follows that the lattice is the free algorithm of n is generated by B, and also the Weyl group is generated by the reflections with respect to B. But in general, the opposite doesn't hold. So, I mean, I'm not researching this. If suppose B generates n, but it doesn't imply that B is root basis. So in the finite case, it's true, but in the, for example, the elliptic case, this doesn't hold. So there is some difference between some linear basis and root basis. And in terms of this root basis, we can define a notion of Coxeter element. So Coxeter element is an element of Weyl group, which is represented by in terms of the root basis in the following way. So here, so therefore, in some sense, root basis is an order basis. So in the finite case, obviously, if we change the order, the resulting Coxeter element is up to conjugation same, but in general it is not. But anyway, so here we actually so therefore here it is not the Coxeter element, but the Coxeter element. So because for one root system, there are several possible choices of Coxeter. So actually, it's probably I'll explain later a bit, but in the affine case, so we will see the example. And so here is definition of the generalized root system. It is nothing but the pair of root system together with the Coxeter. So very roughly speaking, so it is a homological version. It triangulated category with phrase. So if the category is good enough, then by taking glutonic group, one can obtain a generalized root system. And so here I recall the classification of finite generalized root system. So because of the existence of a Coxeter element, generalized root system is finite notion than the usual root system. So in the D case and the E case, there are more than the usual. So in the D case, we have many. So usually D will be divided into several classes, and also there are totally 3 and 5 and 9 types of root systems whose underlying root system are of types E6 and E7 and E8. So these are the Coxeter linking diagram. So once we fix a root basis, then we can draw a Coxeter linking diagram. in the usual way. So I explain a bit. So for each element in root spaces, we put a vertex, and we don't connect two vertices if intersection is 0, and connected by a straight line if intersection is -1, and connected by dotted line if intersection is +1. The last one is not not familiar for something. And so in the D case, so if case 1, so in this diagram, we consider it in this way, and get the usual consider the diagram of type D. So therefore, the type D mu, 1, I often denote by the usual symbol D mu. Now I'd like to explain our problems here. But before, we can easily calculate the characteristic polynomial of the Coxeter element. And it is given by this d mu minus k plus 1 plus dk plus 1. So therefore, obviously, the usual one and the new one our unstandard, non-standard one are not isomorphic because the Coxeter elements are completely different. And now I can say our problems here. So this root system D mu k was first discovered in maybe around the middle of the 80s in the singularity theory, but unfortunately at the time this was not so important because one didn't know how to construct this root system or generalizable system generally. So first problem is to construct this root system generally. And the second one is also a problem. So to usual ADE root system or singularities, one can associate naturally Frobenius on the deformation space of the universal coordinate. But this one, it was not, it is not compatible with this new generalized. But this, so from the viewpoint of the root system, we don't know how to avoid this, or how to say, or distinguish the usual or standard one and non standard. So it's natural to expect there should be some problem structure corresponding to this non-standard one also. So another problem is to construct a problem structure which is compatible with this generalizable system, or more elementary, with some features want to have a problem structure compatible with this characteristic quality. So I'll explain what I want to have me later in our second theorem. And so our purpose today is to explain some affirmative answer to this problem based on the idea that the mu is an type A is an involution. So this is also the basic idea in the randomization part of all form. So there, in order to get D, one considers some polynomial type A together with an involution. So we apply the idea to this situation. Okay, so now first, I'd like to explain a geometric construction of this generalizable system. So consider homological map given by this Laurent polynomial. And the involution which moves certain mindfully. Then from these two data, F and eta, starting from this F, we can consider this short exercise sequence. And here R large R is a Weyl number, positive real number, which is large enough. And also here H tilde then the reduced homological. And from this description, or this one, the description of the reduced homology, so it's the intersection form on this reduced homological we have naturally finite growth system of type to Milnor, but not yet of type D. So therefore, we need involution iota. So this is the first statement with Ikeda and Otani and Shiraishi. And consider the point tuple Ni delta and C. So N is an anti-invariant part of iota of the first relative homological, and define an intersection form or by a symmetrical binding form by using the intersection form on the reduced homological, and consider some all elements of length 2, and they take Otani prism induced by the Milnor monodromy around the circle radius R. Then this double gives a generalizable system of type T mu concave. This is first statement and general construction. Before explaining the idea of proof, I give some comments. So first, consider naively the original one without the iota. Then we can consider another generalizable system, which is of affine type. So by this, from this description, the symmetric binding form, this one, the first homological of the system, it's obviously of rank 1. But this defines a radical of the affine gauge system. And also we can consider a set of roots as a set of all elements of length 2, and the induced automorphism by Milnor. Then we get the affine root system of type H to mu minus k from to k. And by considering the by taking the very roughly speaking the iota invariant part of this, or the so previously one. So here we consider the iota anti-invariant one, and instead, if we consider the iota invariant part, then we get the affine root system of type different a tilde mu minus k from k, and it is described by this Coxeter. So here the double dotted line denotes the intersection minus plus 2. So therefore, between the mu minus k vertex and mu minus k plus 1 vertex, the difference of them define the radical of the root state. And so here, if we change the k, the root basis changes, and they define different generalized root system. So as a root system, they are all the usual affine A type, but by choosing the Coxeter element, they are split into separate classes. This is one remark. And so here I give some idea of the previous statement as our first method. And so consider the zeros of the A. Then f is even function, so f was the one, z to mu minus k plus z minus 2k. So it is invariant under the iota. So therefore, there are mu distinct points on theta such that the zeroth way will be x1 minus x1 and x mu and x minus x. And then consider for each a path from minus x to x, avoiding the origin counterclockwise. So so ER is nothing but, so here 0 and here so we consider some path from minus x to x and denote it by P. And also consider a circle around 0 plus is denoted by delta. Then it's easy to say the iota action on this class of PI is given there. And so by considering the PI minus half of them, this is non-invariant. And it's easy to see that these forms of Q basis of the tensor by Q. And considering the linear combination that then it belongs to the integral class if and only if the sum of NR is an even integer. So in this way, so we get the natural description of the d mu bracket. And once we know the sum, the construction of the lattice and so on, it's easy, or it is like a kind of exercise to have a word basis of the expected form. This is almost all what we need to do. Okay, so starting from the Laurent polynomial f, we could have generalizable system type d mu con k. Now we want to consider some Frobenius structure corresponding to this one. Then we consider the following iota invariant deformation of here we consider we add some monomials which are invariant under iota. So in the last one, so we consider some technical combination of the parameters, but I skipped the explanation today. But it is a natural choice, and it's also based on some experimental result. But anyway, so this we can consider some family problem functions over the problem space N. So it is a little bit different. So I wrote here an example. So here the first one, large the 4.1 is the user some deformation of the so this is the user one variable version of the default inequality, and the second one is the new one. This will be to the form COM2. So we consider a different deformation of different Laurent polynomial. And what we want to do is to construct a problem structure for this definition. So I skipped the definition of problem structure, but it is a couple of product on the tangent street and the non-degenerate similar dividing upon on the tangent street, and some vector field, formal vector fields, small e and large e for the unit vector field and the Euler vector field. And these satisfy certain correspondence conditions and homogeneity conditions. Especially the last one, large E, for the Euler vector field, is introduced so that everything will have suitable degrees. But very roughly speaking, the Frobenius structure is characterized at least locally by so-called flat coordinates and local combination from function for the Frobenius conjecture. So you can call it many things, but you can bring only the flat coordinates and Frobenius potential. And the Frobenius potential is sometimes described as a Generalizable potential. And the one important point is that there is a systematic construction of a Frobenius structure by the deformations from the deformation theory by the use of the primitive form. So some I explain. So you can find this part in our paper with Kyoji Saito. And anyway, a key step is the Frobenius space isomorphism. So what is necessary today is the following. So there is an isomorphism of ON free modules between the tangent sheet and the deformed Jacobian ring. And this iota means the taking iota invariant path. So by this isomorphism, so from the right hand side, we can move the product structure to the left hand side, and also we can the class of 1 and class of large N to define small e and large e, and it is explicitly written in this way. And here, the point is that all degrees are positive. So very similar to the usual ADE case. And so what is necessary is to define non-general symmetry binary form, and it is defined through this Japanese module or something. We often call it just omega. But on this space, on the space of this one form, I'm sorry, I forgot the explanation. So if we consider the category of matrix factorization of A, then the undeformed version of this can be obtained as a coefficient homology. And so one has non-generalized binary form by using the just a residue of this form. So in general, in any variable case, by using the global residue, one can define a symmetric binary form, the non-degenerate symmetric binary form. But in this case, very simple. You can check the non-degeneracy just by calculating the residues. And this omega is isomorphic to the tangent shift, but it highly depends on the choice of the non-real vanishing one. And so each choice gives isomorphism, and by this, in order to define either the non-degenerate symmetric binary form, so it depends on this choice of one. It is the most important point. And so, if this choice is good enough, so more precisely, if we choose a primitive form, then the resulting eta will gives the other data from the structure. And so here's some technical remarks. So we can define as usual of filtered homological, which is let's say almost anyway, so filtered homological and the Gaussian projection only, and the higher residue pairing. And so therefore, by these three notions, we can define a primitive form, and we can define a notion of primitive form, and we can check or we can show the class of the standard form is a primitive form with minimal exponent 1 over 2 times mu minus k, and which induces on the parameter space a Frobenius structure of rank mu and conformal dimension 1 minus 2 over 2 times mu minus k. So so here the number, the minimal exponent 1 over 2 times mu minus k. This is the analog. I'm sorry, I made a mistake. Here 2 times mu minus k is the analog of the usual Coxeter number. Because maybe I skipped that part. Anyway, so this part was a non-real, but this follows from some results by Milnor and Shiraishi and myself and Milnor. Then we have the Frobenius structure, and this is a second main theorem. The Frobenius potential is an element of, so what I want to mean is it is a rational function whose coefficients are rational numbers. This is the first statement. And the second one is the exponents of the Frobenius structure are exponents of the characteristic polynomial by the mu comma k of the Coxeter element. So namely, this one, so this d minus 1 over 2 times mu minus k. The set of these numbers are called exponents of the Frobenius structure, and e to 2 pi that number is 0 of the characteristic polynomial. It is what I want to mean in the second statement. And so here there are another point. So here, this one, this is so the minimal exponent. This is also the important point in the this story or in the theory of primitive forms. And so so because the set of exponents finite set, so therefore there are several choices of the ordering. But if we consider this product structure or the primitive form, the ordering comes naturally from the natural ordering on the rational numbers. So this is a technical remark, but this shows this problem structure is the most natural one for the original polynomial small together with yield. This is the important comment. Maybe so I show the example. So if case 1 and the simple case default, we get so this is in this case it is a polynomial. The Frobenius potential is polynomial.
This is the
yes, exactly, yes. In the one variable version. So, so in this case, the exponent of the coming from the mixed object structure coincides with after something, the exponents of the characters with polynomial and so on. The next one is the non-standard one. The exponents are completely defined from the previous one. And so here in Frobenius potential in the last term, the denominator appears, but still a rational function. So these are the easier examples. And so in the previous example, D4,1, the Frobenius potential was the polynomial, but in general it falls. So of course it is with the Weyl part.
In the case, were these exponents calculated before or we calculate them for the first time?
If case goes on, this is everything's a cluster, the Weyl. But so we calculate it in the, what to say, in terms of the Laurent polynomial in one variable. It is a different point, but essentially the same. So usually, so one considers the or one starts from the polynomial in two variables, but and by considering the deformation of it and then taking a certain, what to say. By completing the squares, we get such a long polynomial. And so, in general, so therefore, if case 1, then the Frobenius potential will be a polynomial. And in particular, we can compare the parameter space with the variable quotient of the calculus subgraph. So, by considering the partial by taking a limit to s to 0, then we recover the whole orbit space. And so in this case, the right-hand side is expected to be a special stability condition for the category of the table. And the second one. So second remark is the following. So the Rubin expected that irreducible. So in this case, I'm sorry, I forgot the comment. But by the construction, it's almost obvious that the Frobenius structure is semi-simple. The product structure is semi-simple, almost everywhere. And the Dubrovin expect that some semi-simple, irreducible semi-simple Frobenius structure with positive degrees, whose Frobenius potential is an algebraic function, should correspond to an irreducible Coxeter group and its Kyoji. So this Kyoji is one of the most same as Coxeter. And in particular, he expected that the cases for the standard one, standard Coxeter correspond to the polynomial Frobenius structure. And this is now already seven by Herting. And so this is our result for the Dubrovin's conjecture for this algebraic function. And also we should say something about the relationship between iota invariant part. So we can consider this map. It's a little technical, but anyway, we can. There is a 2-to-1 correspondence between our moduli, our parameter space, and parameter space for this affine A case. And by considering the iota invariant version of the story. So previously, in our story, we considered the iota anti-invariant version of this. Then in this case, dz of z will be the primitive form. Whose minimal exponent is 0, which induces this parameter space of Frobenius structure conformal dimension 1, which is isomorphic to the one from overforward ground test theory for the overforward P1 mu minus k, comma k. So therefore, the mirror it's important to consider pair of the function and the primitive form, or function and the involution and primitive form. So it determines the tuple determines the mirror of the overforward. So in other words, so instead of dz over z, by taking just dz, then we get another Frobenius structure. And so it is no more mirror of this overforward, but some mirror of non-commutative space. So which is the mu comma k. And I want to say something more. So consider the degree of the so-called Rieschel-Royan number, which takes some coordinate, the so-called canonical coordinate after ordering. Then Arnold and Dubrovin calculated this degree, and they obtained this. On the other hand, the double of this number is the number of all root bases for d mu comma k. So it is given. This part follows from the result by Krugman in 89, and our result. And by combining these two, we get such a number. And essentially, this is expecting the number of fully exceptional corrections up to translations in the categorical sense. And so such a numbers are created to some degree of the number. And so in this sense, because in previous slide, so our parameter space and this and a tilde is 2-to-1, so therefore the double of this number is the degree or just Laurent normal from MD mu comma K. And so therefore, together with this remark, this our promise space also satisfy good property as well. Yeah, you know, it possesses a compatibility test with such as some geometric or algebraic numbers. Okay, so thank you very much. I'll stop here.